Consider this word problem regarding radiant heat. A thin square steel plate, 10 centimeters on a side, is heated in a blacksmith's forge to a temperature of 800 Celsius. I have here a thin steel plate. Ignore the color, it really has nothing to do with this particular word problem. If it gets heated in a forge at 800 degrees Celsius, when I take it out of the forge, it's going to radiate heat back into the atmosphere. But it will radiate heat along this surface into the atmosphere, as well as the backside into the atmosphere. It will also radiate some heat through the thickness of the material, but the thickness in this case right here is, well, negligible. So our word problem, we're going to ignore the thickness, any heat being radiated back into the atmosphere from the thickness, and only concern ourselves with this surface area and the backside. I'm going to draw one side here on the page. And we'll consider this surface A, or side A. Side A. And if I flip it over to the other side, I'm going to consider this one here to be side B. And we're going to ignore the thickness. This particular piece is 10 centimeters long per side. 10 centimeters that way, 10 centimeters that way, and 10 and 10. And the question asks us, if the emissivity is 0.6, what is the plate's rate of radiation of energy? There's also a part B, and I'll do that later on. The equation we're going to use for this one is the radiant heat equation, and it states Q is equal to E sigma A, temperature to 4, times time. Going back to the question itself, it says, if the emissivity is 0.6, what is the plate's rate of radiation? There's that word rate again. And when we have rate, it is something divided by time. So we need to change this into terms of rate. Here's the time. There's the heat. So the rate of radiation, going to bring the time over to the left. Q divided by T, that'll be the rate. A temperature to the power of 4. Now that we have the equation in terms of how we want to use it, the plate's rate of radiation of energy, there's our rate. Let's write down what is given. Looking at the equation, the value of E, that's emissivity, it's given us as 0.6. And it has no units, a dimensionless number. Sigma is the Stefan Boltzmann constant. Sigma is equal to, and that is in the formula sheet. Here it is. The Stefan Boltzmann's constant. 5.67 times 10 to the minus 8. I always remember this as 5678. Minus 8. And the units are joules per seconds, meters squared, Kelvin to the power of 4. Next on the equation is the area. This isn't just any area, it is actually the surface area. And the surface area, that is where the heat is being emitted back into the atmosphere, is that area plus this area, the total surface area. So the area of side A, 10 centimeters by 10 centimeters, plus the area of side B, 10 centimeters again by 10 centimeters. Doing this multiplication and addition, the total surface area is equal to 200 centimeters squared. We look at our constant. On our constant, sigma, the length is in meters, and we have centimeters. So we need to change this into meters in order to match our constant. Changing this here into meters now. 200 centimeters squared, and the conversion factor, 1 meter over 100 centimeters. Follow the units. 1 meter, 100 centimeters. I have to do it twice because it's squared. And the 2 centimeters can all cancel out, leaving me with meter squared, and that's equal to 0.02 meters squared. And that is the surface area. Next is the temperature. Temperature given to us in the word problem is 800 Celsius. Going back to the constant, Stefan Boltzmann's constant tells us the temperature needs to be in Kelvin. I need to change this to Kelvin. 800 degrees Celsius plus 273. I'm going to ignore the 0.15. Just ignore that part, just use the 273. And the temperature is equal to 1073 K. We now have everything that we need in order to solve this problem. Oh, lastly, write down what it is that we're looking for, and that is the rate of heat being dissipated back into the atmosphere. Putting all of that into the equation now, I'm going to start way over here on the left-hand side for rate of heat. Rate of radiation energy is Q is equal to 0.6, and the Boltzmann's constant, 10 to the minus 8 joules per seconds meter squared Kelvin to the power of 4. All of that times the surface area, which we calculated to be 0.02 meters squared. Multiply that times the temperature to the power of 4, which we said is 1073 Kelvin, everything to the power of 4. We need to remove this power. In order to do that, this 4 operates on the number as well as the units. And it will look like this. I'll just rewrite the whole equation again. The rate of radiant energy is equal to 0.6, 5.67, 10 to the minus 8 joules per seconds, meter squared, Kelvin to the 4, 0.02 meters squared. And rewriting this one without the power is 1073 to the power of 4, temperature to the power of 4, removing the brackets. And everything here is multiplied. Looking at the units now, we got this, my mistake, this is Kelvin to the power of 4. Looking at the units now, Kelvin to the power of 4 will cancel out. Meters squared will cancel out. And a joule per second is the same as on the left-hand side. Energy is in joules, time is in seconds. So a joule per second on the left-hand side. So the right-hand side in units matches the left-hand side of the units. All is good. Nothing left to do now except take all these numbers, being careful with this one here to the power of 4, and place them in the calculator. The rate of radiant heat then is equal to 901.9 joules per second. And a joule per second is also known as a watt. Reducing this to two significant figures. Looking at what we have here is 2 sig figs there, 2 sig figs, ignore temperatures as I said in the past. 9.0 times 10 to the power of 12 squared watts. For all intents and purposes, I'll just simply call this guy 900 watts. Watts is a unit of power. Another way of saying this, the radiant power going back into the atmosphere once this particular item has been heated to 800 degrees Celsius is 900 watts. Let's look at part B. What temperature would be required for this plate to radiate at a rate of 1500 watts? I'm going to carry on a separate sheet. Moving on with part B. Equation we're going to use is the same. The rate of heat dissipation is equal to E sigma A temperature to the power of 4. What temperature? We want to find temperature now. Putting in the values that we already know from the previous page. 1500 watts, that's this one right here, so the rate of power is 1500 watts, is equal to 0.6, and the Stefan Boltzmann's constant per seconds meters squared Kelvin to the 4. Multiply that times the area, and temperature to the power of 4, that's what we want to find. Everything here is multiplied. In order to isolate t to the 4, I'm going to take these three terms and divide it into the left-hand side. And it will look like this, 1500. And instead of using a watt, because it has a tendency to hide units, I'm going to open it up into joules per second. Divided by 0.6, dimensionless value, 5.67, 10 to the minus 8, joules per seconds, meters squared, Kelvin to the 4. And 0.02 meters squared is equal to temperature to the power of 4. Looking at the units in the denominator, meters squared will cancel out. Joules per second and joules per second also cancel out, leaving Kelvin to the power of 4. I'm going to leave the Kelvin down here. Doing the mathematics, 1500 divided by the 0.6 and these other terms, the answer is 2.2045, 10 to the power of 12, divided by, and the Kelvin to the power of 4, it's 1 over Kelvin to the power of 4, 1 over Kelvin to the 4. It's a fraction. There's a unit of 1 always on the top. And that's equal to temperature to the power of 4. To bring the unit back up to the top, you're going to invert and multiply. Just like two fractions, if this here is divided by 1, so it's a fraction divided by a fraction, invert and multiply. Doing so, 2.2045 times 10 to the power of 12. Inverting and multiplying makes this guy 10 to the power of 4 over 1 is equal to temperature to the power of 4. So we're in Kelvin. We can ignore the 1 in the denominator. Here's our answer, to the power of 4. In order to get just simple temperature, we need to take the fourth root of everything. Fourth root of the left-hand side, fourth root of the right-hand side. And it will look like this, taking 2.2045 times 10 to the power of 12. Kelvin to the 4. The units go with the number. And we'll take the fourth root of that. Whatever I do to the left-hand side, I have to do to the right-hand side. Temperature to the power of 4, fourth root. The number, after taking the fourth root of this value, is 1218. And Kelvin to the power of 4, the fourth root is Kelvin. It's equal to the fourth root of temperature. 4 is T. Reducing this to Celsius. The conversion equation for Celsius is on the formula sheet. Here it is here. To find Celsius, it's Kelvin minus 273. Taking the value of Kelvin. That's equal to 945 degrees Celsius. rounding that to 2 sig figs, approximately 950 degrees Celsius. Therefore, temperature of approximately 950 degrees Celsius is needed in order to radiate at a power of 1500 watts.